All right, so this video is like a part 2 to the should I upgrade my fuel pump or should I use a voltage booster on my factory stock fuel pump. All right, so here I already have the data. I erased the stock voltage OEM pump data, '05 Mustang OEM pump data. Here is the voltage booster data. So I have the 40 psi data, 15.5 amps, 1.3 gallons per liter, 295 liters per hour, and 271 watts. And then the 50 psi data, which was 16.1 amps, 272 liters per hour, 281 watts. So I have this is the common pump I recommend for stock block upgrade. It's the kit I sell the most of, the 400 liter per hour Ti Auto F90000262 pump. So let's turn that on. Get her going. Let's put her at that factory 13.5 volts. Ooh, simmer down now. All right. And let's go to that same 40 psi of pressure. Here we are. 40 psi. Yep. Okay. Bouncing up to 1.8. We'll give her the benefit of the doubt and call her 1.8. Stay, phone. Cool. All right. So amperage on the 400 liter power pump, we are at 14.6. So less than that factory pump strolling boosted. And flow said it was bouncing up to 1.8 to 1.7. I mean, yeah, let's just call it 1.8. So 1.8 times, let's convert gallons per minute to liters per hour to 27.125. 408.8, 409, whatever, 409 liters per hour potential at 100% duty cycle, full on, right? Obviously we'd be returnless, we're just comparing full on voltage, right? So let's do some comparisons percentage wise. 15.5 amps minus 14.6 amps, it's 0.9. Divided by 14.6, 6%, 0.06. So 6% less current draw. And then we gained flow. So 409 liters per hour minus 295. We gained 114 liters per hour of flow. And then let's divide that by 295 to get the percentage, 0.38. And we gained 38% more flow. And that's before we even look at the 50 psi, if we're just comparing the 40 to 40. It's clearly better. I'm drawing a little less current, 6%, about an amp. But I have 38% more flow potential to support the power. So whereas the BAP on the factory pump to try to get to 500, which it's going to struggle, like some guys, depending on your power hour setup, you'll max this, you'll peg this at 100% duty cycle. Might not even get to the power you want in the upper RPM range, because that's a little low, 295. I would want to see more, but you have more flow potential, so your pump's going to be a lower duty cycle, right? So even these numbers will actually look better in the car, because you're not even going to... At 100%, it's better. And it's going to be at a lower duty cycle in the car, which is going to make it even better. Does it make sense? Pretty straightforward. Let's go ahead and do the 50 psi numbers, because that's going to be a real test, right? 500 real horsepower power outer setup on a 3 valve. I'm putting 10 pounds of boost in the manifold. The PCM is going to have to raise 1-for-1 to 50 pounds of fuel pressure, so the injectors can still deliver the correct amount of fuel and overcome the boost in the intake manifold, right? So let's dial her back up to 50. I'm gonna get right on 50. Ford regulators are amazing, by the way. They have very fine pressure control. Easy to dial in exactly how you want. All right, so we're at 50 psi. All right, so my current draw went up, my flow went down, which is normal, right? So the higher the physics is, the higher the fuel pump outlet pressure, the more, back pressure on the pump outlet, the flow goes down. That's the physics of it. So we're down to 1.6 and 15.6 amps of current. So let's compare those numbers at 50 psi. So amps, 15.6, still less, and flow 1.6 gallons per minute. Let me convert that real quick. 1.6 times 227.125 equals 363 liters per hour. So 363. So this is at the 50 psi, the actual pressure you're going to be running the car with boost. Average setup 10 pounds of boost, right? So 363 liters per hour potential, vice 272, and I'm still about a half amp less current draw. It's still better, right? And that's assuming max duty cycle. Again, I'm going to be at a lower duty cycle. Actually, I might try to simulate that here at the end. That'll be kind of cool. I think I know how I can do that. Well, let me look at my percentage differences again. So we'll go 16.1 amps minus 15.6 is 0.5 divided by 15.6. Not much, 3%. So 3% less current. And then our flow, 363 minus 272 is 91 liters per hour divided by 272. 0.33. 33% more flow. Let's do the watts. All right, so watts is voltage times current. So at 13.5 volts times 15.6 amps, I'm creating 210 watts of energy or power heat. And then this one was 281. So let's look at that percentage difference. 281 minus 210, 71 watts divided by 210. 0.33, also 33%. So 33% less heat, watts, power, energy created, put into your gasoline, right? So, it's a submerged pump, the fuel cools it, so, it's not working as hard. It's easier to cool, it's not generating as much heat. Pretty cut and dry. I can tell you which one's more efficient, which one's safer, which one gives you more overhead. And yeah, for that last part, let's simulate like a duty cycle, right? Because I'm not going to be maxing out this 400 liter per pump because I have so much overhead. Typically, you want to, for a pump, 90% max duty cycles are good. So let's say 10%. You want to, 90% allows for wear in the pump over years. your fuel filter clogging over time, creating more back pressure. That 10% safety buffer is just an industry kind of recommended, like, hey, try to keep your pump under 90% duty cycle. That way, when you do your data logs or your tuning, okay, my pump's at 90%, I know I'm good for a long time. Doesn't mean you should neglect filter maintenance and stuff, but you have that buffer or safety margin that so as the pump wears and the filter clogs, you're not going to immediately peg the pump and go up to 100%, lose fuel pressure and lose air fuel control, right? Safety. We like buffers. Everyone likes buffers. So we said 90%. So I'm going to take, and that percentage equates straight to voltage, because when you're pulse modulation, you're ground switching to lower the actual voltage the pump sees based on duty cycle. So I'm going to go 13.5 volts times 0.9, 90%. So that gives me 12.1 volts. So realistically, if I keep this pump 90% duty cycle or less, the most voltage it's going to see is 12.1 volts. So it's dialed down to 12.1 volts. 12.1 volts, let's get there. Alright, 12.1 volts. So if I'm running this to 90% duty cycle, I'm at still 1.3. I thought I saw 1.3. So I still have efficient flow. So going down, not needing the full 13.5 at just 12 volts, 90% duty cycle, that pump is still in its operating range to be efficient. It's still flowing the same amount. Still flowing 1.3. Yet, now I'm drawing less current. I'm 14.3, 14.4 amps. Right? And that's at that same 50 psi. Actually, because I dialed the voltage down, pressure changed a little bit. Let's dial that up a tad. Get back to that 50. Want that solid 50. Now we're bouncing to 1.2, 1.3. I mean, we still have really good flow. The pump's efficient, right? It makes sense. So, to wrap this up, yeah. You decide what you want to do. I can tell you, the data can tell you 100%. It is safer and more efficient and cost effective to put in a brand new higher flowing pump, vice increasing voltage to your stock pump. All right, this was a cool one. I like the data from this one. All right, that's it. Thanks.